In this video, we're going to be learning about Dalton's law of partial pressures. When we've been talking about all these gases and gas laws, we have just been talking about moles of gas. And so we never really specified what that gas was. Was that gas a pure substance? Was it a mixture of different substances? And the truth is, it really doesn't matter because we just need moles of gas. That gas could be all one gas, or that could be a mixture of gases. Because at the same temperature and pressure, if these are two identical containers, if they have equal numbers of moles of gas inside, they're going to have the same pressure, even if one is a mixture of gases and the other one is just a pure substance. When we talk about partial pressure, we're specifically talking about a gas mixture, and we're trying to figure out what pressure is due to this substance that I'm circling now versus the other substance. So how much of the whole pressure is due to that one component of a gas mixture? We can take the pressure due to one substance, the pressure due to the other substance, and then those add up together to be the total pressure. Most of the time we know this total pressure and then we backwards calculate what the partial pressures were from that. So this is Dalton's law of partial pressures. It says that the total pressure of gas is equal to the sum of the partial pressures of each component. Here's an example of how that works. Here are equal volume containers. There's gas A at a pressure of 300 kilopascals, gas B at 600 kilopascals, and gas C at 450 kilopascals. And then somehow they're all combined together into one container together, and we're asked to find the total pressure. To find the total pressure, we add up the pressures of A, B, and C. And so that's going to be 300 kilopascals plus 600 kilopascals plus 450 kilopascals. So 300 plus 600 plus 450. And so this is 1,350 kilopascals. Here's a practice problem for you. The contents of two 5-liter containers, one containing H2 and the other containing helium, are combined as depicted over here. What is the final pressure of the 5-liter vessel? There's volumes and temperatures down here. Go ahead and pause the video and work this out. Unpause the video when you're ready to check your answers. Okay, so to get the total pressure, we're really just going to be adding these two pressure amounts together. That's way faster than applying PV equals nRT, which we could do. We could find N total and work out 1.75 moles and plug that into PV equals nRT because we're given volume, we're given temperature, so we totally could work that out. Or we could just add those together. And so that's going to equal 8.4 atmospheres. So there was this other way of solving it because you were given enough information to solve it using that method. So let's talk about another way of solving for partial pressures. We know that the pressure of one component of a mixture would be due to the moles of that component. So the total volume of the container is what the volume of that gas is. But to solve for the partial pressure of component A, we can look at the moles of that substance times R times T, and then the total volume of the container. We also know that we can solve for P total by adding up the total number of moles times R times T, and then dividing by V total. Because if we took all these different partial pressures, we could add that up. And by adding up all these different partial pressures, we're essentially just adding up the total number of moles. Now look at this equation and this equation. You can see that they have some variables in common. And so what happens if we divide this equation by that equation? So if we divide PA, NA, RT over V total by the second equation down here, because math lets us do that, then my V totals are going to cancel out, my RTs are going to cancel out, and then I'm just left with PA over P total is equal to NA over N total. This is what we call the mole fraction, which is given a symbol X, and that's going to be the mole fraction of A. So the mole fraction of A is going to be the moles of A divided by the total number of moles in the container. So we can take this, in order to solve for our partial pressure of A, we can multiply both sides by P total, bringing the P total over here, and then we end up with this equation, where the partial pressure of A is equal to the mole fraction of A times the total pressure. So here's a summary of different ways that we can solve for the partial pressure of a gas. The partial pressure of a gas will be equal to the total pressure times the mole fraction, or the partial pressure can be calculated by looking at just the moles of A times R times T divided by the volume. So in a lot of ways, this mole fraction is like that mass percent composition, only it's in moles, not mass, and it's in more of a decimal fraction format rather than a percentage format. Let's go over an example of calculating that mole fraction. This problem reads a 0.25 liter flask containing 0.150 moles of A and this many moles of B is at this temperature. What the total pressure in the flask is blah. What are the mole fractions of each gas? So I'm given a lot of extra information that I do not need to solve for the mole fraction, but I am just asked to solve for the mole fraction. So let's do that. I have 0.150 moles of A, and then the total moles will be equal to 0.150 plus 0.350 moles. Just adding up the moles of the component mixture. And then that's going to add up to 0.50, and get my calculator. Okay, so once this is calculated out, this will be equal to 0.300. There are no units on this because moles divided by moles is no unit. Next, we can repeat the process for B. The moles of B is 0.350 moles, and the total number of moles is the same as here, and so that's 0.500 moles. And then that's going to equal 0.700. Again, no unit. These, remember how percentages add up to 1? These are decimal formats, and so they should add up to 1. Here's a practice problem for you. Go ahead and solve this in your notebook and unpause the video when you're ready to continue. You're supposed to be finding the partial pressures of each mixture in the gas. Okay, so we know from the past slide that the mole fraction of A was equal to 0.300, and the mole fraction of B was equal to 0.700. So to find the partial pressure, what we can do is take our mole fraction and multiply it by the total pressure. So let's see, what's the total pressure? The total pressure is given to us right here. And so that means that we have our total pressure. So our partial pressure of A will be equal to my mole fraction of A times my total pressure, 496 kilopascals. My partial pressure of B will be equal to 0.700 times my total pressure. So 0.3 times 496, and that is 148.8 kilopascals. 0.7 times 496 is equal to 347.2 kilopascals. I need just 3 significant figures on each of these, so I'm going to round that to 149 kilopascals, and I'm going to round this to 347 kilopascals. And that gives me my partial pressures of each gas. The other way that you could have done this would have involved just taking the moles of A, which is 0.150 moles, multiplying that by R. I'm going to use the one for atmospheres, and then I'll convert my answer into kilopascals afterwards. Bigger atmospheres per mole Kelvin. And then my pressure, or my temperature, I have to add that to 273.15, and so that's 298.15 Kelvin. And then dividing that by the volume, which is 2.50 liters. Then this is going to give me my answer in atmospheres, and so I'm going to cancel out my atmospheres and go to kilopascals. And so I'm going to say for one atmosphere is 101.325 kilopascals. And when I calculate that all out, I do end up with 148.738 kilopascals, which when rounded to 3 significant figures is still 149 kilopascals. So you can see that that's another way of solving for the partial pressure of gas A. Here's another practice problem for you. This one should be a little bit more conceptual in nature. It says a gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3.0 atmospheres. What are the partial pressures of helium and neon? You should be able to do this in your head without the aid of a calculator. Unpause the video when you are ready to check your answer. Okay. So if there are equal numbers of helium and neon gas, that means that the mixture is half helium and half neon. That means that I can take this 1/2 and 3.0 and multiply them together. And so helium and neon both have partial pressures of 1.5 atmospheres. Here's another practice problem for you. This one will involve calculations, so you will need to have your calculator out. It says a sample of gas contains this many moles of nitrogen, this many moles of oxygen, moles of argon, moles of carbon dioxide, and then you're given the temperature in Celsius and the volume of the container, and it wants the partial pressure of oxygen in bar. Go ahead and pause the video and work this out. Unpause the video when you're ready to check your answer. Okay, so I know that my partial pressure of oxygen is going to be, my partial pressure of oxygen is going to be equal to my moles of oxygen times my R times T divided by my volume. That's my ideal gas law. And so my moles of oxygen are 2.095 moles of oxygen. And then since it wants my pressure in bars, I'm going to use this value of R. That way my unit of pressure will be in bars in the end. And so at 0.08314 liter bar per mole Kelvin. And then my temperature is going to be 298.15 Kelvin. And then my volume is going to be 20.0 liters. So let's type that into my calculator. 2.095 times 0.8314 times 298.15. Divide that by 20. And that gives me 25.96 bar. I had not typed in that 0 into my calculator. That's important. It is 2.5965 bar. And then I'm going to need 3 significant figures. And so it's going to round up to 2.60 bars. You could have gone through and found the total pressure by adding up all the different moles of gas and then finding the mole fraction and the total pressure and multiplying the total pressure from the mole fraction, and you would have ended up with the same thing. I think this way was a bit faster. So once you understand partial pressures and the different methods of calculating them, you can decide what is the fastest method to solve the particular problem that you're solving, given the information you're given. Are you up for a challenge? Well, this is a challenge problem for you. So this is to review our limiting reactants. So once the stopcock between these two vessels is opened, the gases will combine to react, and the reaction will go according to this balanced reaction here. And then the problem reads, after the reaction, what is the partial pressure of the remaining reactant? You can see that they're starting at different pressures and different liters. So you have to figure out what is the limiting reactant and how much of the excess reactant is left so that you can figure out its partial pressure in the end. Go ahead and pause the video and try to work this out, and then you can check your answer soon. So let's go over how you would solve this problem. So the first thing we need to do is figure out how many moles of each gas we have. We can apply the ideal gas law to each individual container, and we find that we have 0.1238 moles of nitrogen monoxide and 0.1440 moles of oxygen gas. Then we have to figure out what the limiting reactant is. Since we're trying to figure out the partial pressure of another reactant, rather than calculate the amount of a product that we're going to make, I'm going to pick one and then calculate the amount of the other reactant needed to react with all that stuff. So I picked oxygen, and I'm going to use this amount of oxygen to calculate how much of that was needed. So this is the amount needed, and then I compare how much do I have versus how much I need. I do not have enough. This is less than that. So that means to me that I do not have enough. That means the nitrogen monoxide is going to be the limiting reactant. And that means I'm going to run out of the nitrogen monoxide. And that means my oxygen is going to be in excess. So now I have to figure out how much oxygen is in excess. How much is left after this reaction is complete. To do that, I have to calculate how much oxygen reacted with the nitrogen monoxide. So I'm going to take my limiting reactant here and calculate how many moles of oxygen gas are consumed in that reaction. And I calculate that I have 0.0617 moles of oxygen gas used up. I started with this much oxygen gas. I'm using up this much. How much is left? I can do a simple subtraction to figure out how many moles of oxygen gas are left over. And this is how many moles of oxygen gas are left over. Now I can figure out the partial pressure of that oxygen gas in the container by applying the ideal gas law with this molar amount. The two containers are now combined, and so the effective volume of the container is 8 liters. That gives me a partial pressure of oxygen gas of 0.2500 atmospheres.